Welcome back. Now we are going to study about second part of the lecture, generalized Pauli's principle, release exclusion principle. This has two parts, NN system and generalized Pauli system. First, let us study NN system, neutron system. Now this system can be studied either by NN scattering or by other methods. Now, studying NN system by scattering process is slightly difficult one, although it is not impossible, because obtaining neutron as a target is a highly difficult thing. Therefore, here instead of going experimental study, we choose other methods of studying NN system. So to study the effect of NN system, we consider mirror nuclei of simple system like containing only 3 nucleons. The examples for 3 nucleon systems are triton, which is the isotope of hydrogen H3, and helium, which is the isotope of helium, containing only 3, helium 3 nucleons. So these two systems are represented by 3 particles H3 and helium 3 as left part of this is actually hydrogen 3 and right part of this is helium 3. Hydrogen 3 contains 2 neutrons and 1 proton. Helium 3 contains 2 protons and 1 neutron. Both, if you observe clearly and carefully these figures, you can notice that both of these two systems contains 2 NP bonds and 1 NN bond in the case of H3 and 1 PP bond in case of helium 3. So those two are denoted here in the just below of these two diagrams. So this has 3 bonds, 2 NP bonds and extra bonds, 1 NN bond in H3, 1 PP bond in helium 3. Keeping those information in mind, we can then estimate the binding energies of these two nuclei separately, as the first one here is actually for hydrogen 3, binding energy of hydrogen 3, which is equal to 2 times energy of 2 times NP bond plus energy of 1 times NN bond. For helium 3, it is energy of 2 times NP band plus energy of 1 times PP band. So taking the difference between these two binding energy, we can get difference in binding energy delta B as the first part is common in both of these two equations. If you take the difference, those two will get cancelled. Then what we have is only this. This one, EPP minus ENN. Now PP system has Coulombic interaction as well as nuclear interaction. So if you separate PP Coulombic interaction energies and you then consider only E nuclear interaction of PP system and NN interaction of energy of NN system. NN system can have only nuclear interaction. So in this expression 11, delta B is measurable quantity experimentally, and first part of and the RHS of 11 is estimatable. So that can be estimated accurately using this expression, because only Coulombic interaction just requires magnitude of charges and separation distance between the two particles. So that can be estimated accurately. So if we can estimate this and that, then we can inform about these two systems, EPP nuclear minus ENN. Now, if you do all the calculation, you can show that EPP nuclear difference with the ENN is nearly equal to 0. So that implies actually, if you extract energy from that, the nuclear force between proton-proton system is nearly same as nuclear force between neutron-neutron system. So from the PP scattering theory, we have just learned that nuclear force of pp4 system is nearly equal to nuclear singlet force of NP system. So combining these two equations, we can write nuclear force PP is nearly same as nuclear force of NS, which is nearly same as nuclear force of singlet system of NP, singlet NP system. Now this actually tells that charge independence of the nuclear force. So nuclear force doesn't differentiate between whether it's a charged particle or uncharged particle. It's same between neutron and proton, neutron, neutron, and proton, proton. In other words, nuclear force is blind to charge of the particle. Then, with respect to nuclear force, how one can differentiate between a neutron from the proton, the two nucleons. In order to differentiate between the two nucleons as far as nuclear force is concerned, another quantum number is defined, which is called as isospin, denoted here as small t, to distinguish between neutron and proton. So since the degeneracy of nucleons is 2, because there are only two particles, neutron and proton, in isospin doublet, that can be equated to 2t plus 1 and can be obtained the value of t. T equals half. This t equals half is same for both the nucleons, for proton as well as neutron. However, the third axis projection of isospin is different for two particles. It is plus half for proton and minus half for neutron. T3 is third axis projection of isospin. When two nucleons are coupled, the total isospin is written as T1 plus T2. If there are only two nucleons, then this T can be written as either 0 or 1. 0 refers for isospin singlet and T equals 1 represent isospin triplet respectively. This isospin is a quantum number and it is a conserved quantity in strong reaction at least. Then with the inclusion of this isospin, Pauli's principle can be generalized for such non-identical particles. Remember, this generalized Pauli principle is applicable for non-identical particles. Now, generalized Pauli's principle says that the total wave function must be antisymmetric for fermions, whether it's for one particle or two particles, for nucleons, for atoms, for other fermions. So this generalized Pauli's principle holds good only for nucleons because the nucleons have isotopic spin, a new quantum number. Now this total wave function is a product of three wave functions: spatial wave function, spin wave function, and isospin wave function, which is denoted as tau iso. So therefore, generalized Pauli's principle total wave function is written in this manner. Now this Pauli's principle requires that total wave functions to be antisymmetric. Now phi space in that wave function represent spatial wave function, which is characterized by total angular momentum L. It basically characterizes the spatial part. So this L can take two different set of values, 0, 2 for symmetric wave function, 1, 3, 5 for antisymmetric wave functions. Similarly, chi spin wave function is characterized by total intrinsic spin S, and for two particle system, it can be either spin triplet or spin singlet. Spin triplet is identified as symmetric and spin singlet is identified as antisymmetric. Exactly on similar line, isotopic spin is characterized by total isospin T, capital T. Now it can have, for in case of two particle system, it can have isospin triplet or isospin singlet when the two spins are in the same direction. Then it's called symmetric. When the two spins are opposite direction, it's called antisymmetric. So this is a general information about generalized Pauli's exclusion principle. Now the spin triplet state is symmetric with respect to exchange of two nucleons, whereas spin singlet state is antisymmetric. This is a very general discussion. Now since total wave function to be antisymmetric with respect to exchange of any two new fermions, including nucleons, it requires that this number L plus S plus T should be added. Otherwise, the wave function will not be antisymmetric. So that can be written in terms of parity, and parity will be equal to minus 1 to the power of L plus S plus T. This is the parity for generalized Pauli's principle. Basically, that defines whether the wave function is symmetric or antisymmetric. Now for nucleon interaction, N capital represent nuclear interaction. To be a bound state, only if the two nucleons exist in L equals 0 and S equals 1 state. This is what we have understood from the earlier studies of neutron. So generalized Pauli's principle implies then T to be 0, a isospin singlet state, in order to have total wave function to be antisymmetric. So I'm going to list a table. In that list, we are going to list two parameters, namely scattering length A and effective range G for the two nucleon pulses. So two nucleon pulses can be between neutron, between proton, and between a neutron and a proton. So we can have many such combination for isospin triplet and isospin singlet. Isospin singlet can have only one value, whereas isospin triplet can have three values as shown in this table. Now carefully observe this table. For isospin triplet, this one, we have three values. For isospin singlet, we have only one value as shown here in the below this column. Now here, for A value in this table, you can find that all these A values are negative, whereas when isospin singlet in the case, the A value is positive. Note that. Second thing, A value scattering length is nearly same for PP and NP system, and it is different from NP system. And this effective range is almost same for all these cases. Now keep that in mind. We can list some of the information from the table. For spin singlet state, which corresponds to isospin triplet state, there is no bound state because A is less than 0. Scattering length is less than 0. And for spin triplet state, which corresponds to isospin singlet state, only one system exists with A greater than 0. A greater than 0 implies that's a bound state, and we know that state corresponds to, that system corresponds to a neutron. Also, the two values of scattering length for NP system for T equals 0 and T equals 1 are different. So this clearly indicates that the nuclear force is a isospin dependent. So this is an additional quantity or additional information what we can obtain for nuclear force. So nuclear force is isospin dependent. So in this lecture series, we have proved many things. We have proved nuclear force is short range, we have proved nuclear force is spin dependent, we have proved nuclear force is charge independent, and here from this we are proving that nuclear force is isospin dependent. So that's about the generalized Pauli's principle and NN system, and that ends the lecture. And thank you for your patient hearing.